So does it work? That was the first attempt, and since then there's probably been attempts every year. So every year you get papers published on this topic, and for every paper that is published, you probably get 10 or 20 papers that don't get published. People who tried but didn't even manage to publish anything. And they looked at different ways to introduce dependence. And the sad thing is you never get any consistent improvements out of these attempts. So you only get sort of promising results type papers. So what's going on? It seems like 1977 was a long time ago, and it's plenty of time to find a workable approach to a good idea. And this seems like a good idea. Like modeling dependencies is a really good thing in all the fields that are adjacent to search engines, right? So you ask any natural language processing guy, is it good to model dependence between the words? And they'll start jumping up and down, and they'll be very adamant about it. Right? In some fields, you get nowhere if you don't model dependencies between the words. So if you try to recognize speech, and you try to do it with a unigram model, without a Markov chain, without a language model, good luck. You're never going to get anywhere. If you try to do machine translation and you don't have a language model, you don't condition word on other words, you're going to get gibberish as output. So in those fields, it's absolutely critical to model dependencies. And here you have a field that for 3 decades hasn't been able to make it work. So what's going on? Now, one possible explanation for what's going on is in those other fields, so the field of speech recognition or the field of machine translation, the task involves producing new strings of text. Right? So in speech recognition, you get a waveform, somebody recorded their voice, and the goal is to produce a transcript. A transcript is a new string of text. It's something that you haven't seen before. And that string better be grammatical. And that's why you need word dependencies in speech recognition. Same thing in machine translation. I give you a sentence in Swahili, you want to come out with a translation into English. That translation could be completely new, you might have never seen it before, but it still needs to be grammatical. In information retrieval, you are dealing always with strings that are already well formed. Right? Documents were already written by humans, and queries are written by humans as well. So you don't really need to waste your probability space on trying to make them well formed, and that's what dependency models do in some way. So that's one possible explanation for why it doesn't work. You're wasting your probability space, your parameter space, on things that you don't need. They're not really part of the task. Another explanation, and this is slightly controversial, is that the model itself really doesn't assume independence. Now you look at it and you say, wait, we did. You remember that assumption, right? We very explicitly assumed independence. So what we showed is that independence is a sufficient condition, but is it a necessary condition? So could you come up with a weaker assumption that is sufficient to derive the model? And it turns out that you can, and we can show it for a first-order dependency model like the model of Van Rysberg, and it's a little harder for higher-order dependencies. So this is the model without any dependencies, right? We're ranking documents by the ratio of the probability of the document vector under the relevant class and under the non-relevant class, right? And if you assume word dependence, then this factors into the following form. So you have P1, that's the probability in the relevant class of DW, and DW can either be 0 or 1, depending on whether the word occurs or doesn't occur in the document. And for the same event, DW, we have P0, the probability of that event under the non-relevant class. And so that's your model without any dependencies. That's really assuming independence. In Rysbergen's model, or in any other model that assumes first-order dependence, paired dependencies between the words, your ratio looks like that. Right? Now you are taking the event of the word W occurring or not occurring in the document, and you're conditioning it on that parent, pi W, occurring or not occurring in the document. And you're doing a product over, and for now, let's say over the whole vocabulary. So, on the left you have the product when you assume independence. On the right you have a product when you don't assume independence and you replace it with first-order dependencies. Okay. Now, under what condition would these two things be equal to each other? We can come up with a factor k, and we're going to have two of them. We're going to have one for the relevant class, one for the non-relevant class. That if you take the left side and you multiply it by a product of these factors, you're going to come up with exactly the thing on the right side. Right. So what are those k's? What those k's are, so r can be 0 or 1, depending on whether you're doing it for the relevant or the non-relevant model. I'm going to have a ratio, and at the top I'm going to have a joint probability between the word and the parent of the word. Right? So the event dw for the word itself and the event d pi w for the parent of the word, that's the joint probability of those two events happening in the document. And on the bottom, I'm going to have the product of the independent, sort of the product of each event independently of each other. So P of dw probability for the word event times the probability for the parent of the word. Okay. Now, just check for a second that taking k1 of w and putting it here would give you the right thing. So think about what happens. I have a joint, and I divide it by the probability of the word itself times the probability of the parent. Okay? When that factor appears in the numerator in the second product, it's going to combine with that probability right there. So that probability for the word itself is going to cancel that part of the ratio, and what I'm going to be left with is the joint divided by the probability of the parent event, and that is the definition of the conditional probability. Okay? So if I multiply that probability by the factor, I get exactly the conditional probability, the probability of the word occurring and not occurring, depending on whether its parent occurred or didn't occur. And you can verify that it's the same for the K0, for the non-relevant class. So now I know that if I multiply the left side by this factor, by the product of these factors, then I'm going to get exactly the right side. Okay. Now, what happens if that factor kw was the same for a given word for the relevant and the non-relevant class? Right. So if it were the same, if it just happened to be that they were the same for every word, then this product would multiply out to 1. Right. So in this case, you would get exactly the same performance between a model that assumes independence and a model that assumes first-order dependence. Now, what does this factor mean? To figure out what it means, we need to actually think about what is that factor. What is it? To compute that factor, we took the joint between the word and the parent and divided by the marginals for the word itself and for the parent itself. Now, suppose that there really was no dependency between the word and the parent. In that case, the joint would be exactly equal to the product of the marginals. So in that case, yes, if the events were truly independent, then KWs would come out to 1, and you would have left side equal to the right side. That would be independence assumption. But we don't need KWs to be equal to 1. We just need them to be equal across the class boundary. So KW could be a large number. The word could be highly dependent on its parent in the relevant class. But as long as it has the same exact dependency in the non-relevant class, K1W and K0W are going to be the same number, and the product is going to multiply out to 1. So what it means is you don't need to assume independence. You just need to assume something called linked dependence. You can have a dependency between a word and its parent just as long as it's the same dependency in the relevant class and in the non-relevant class. All right, great. So this is pretty good. What we're saying is independence is not a necessary condition. It's sufficient, but we can make a weaker assumption, linked dependence, and still have equivalent performance. But it turns out we can actually do better than that. Right. What we really want is we just want that number to not affect the ranking. We don't care, like, if K1W is the same as K0W, yes, that number will integrate to, will multiply out to 1 and it will not affect the ranking. But there are lots and lots of other ways in which it couldn't affect the ranking. What you really want is you just want the product of all the KWs for the relevant side to be the same as the product of all the KWs for the non-relevant side. That means that some KWs can be bigger in the relevant class than they are in the non-relevant class, as long as that is balanced out by some other words which are more codependent in the non-relevant class than them in the relevant. So if overall that whole product goes to some constant that is independent of the document, this factor will not affect the ranking. So one way to write it out is if you multiply out the factors for the relevant side and for the non-relevant side. So on the left, you can think of that as the aggregate, the total amount of interdependence between the word and the parent under the relevant class. And this is the same quantity, the total aggregate amount of dependence in the non-relevant class. And as long as those are proportional to each other, as long as they will not affect the ranking. So that assumption is a lot weaker than assuming independence. So if that's confusing, so here's a specific example. What is independence? Independence means that you're in a document, you see the word Obama, that tells you absolutely nothing about seeing or not seeing the word Romney. Right? That's independence. Seeing, absence, or presence of one word tells you absolutely nothing about presence of another. Linked dependence, that's where K0 is equal to K1. That says that seeing Obama can increase your chances of seeing Romney. Right? So they get to be dependent. But they must be dependent to the same amount in the relevant class and in the non-relevant class. The proportional interdependence says it doesn't have to be by the same amount. So seeing Obama can increase or decrease your chances of seeing Romney however the data wants it to happen. And they can be more codependent in the relevant class than in the non-relevant class, as long as some other words balance out that dependence. So maybe Obama and Romney are codependent in the relevant class a lot more than in the non-relevant class, which would happen if the topic is the US elections in 2012. So as long as in the non-relevant set some other words balance out that imbalance, everything is going to be okay. So for example, if world and COP are more codependent in the non-relevant documents, then that will help balance out the Obama and Romney in the relevant class. Okay. So the point is that assumption is a lot weaker than assuming independence, and that is what is necessary for the model to be as good as any first-order dependence model that you can come up with. So that's one possible explanation of why modeling dependence doesn't really bring anything to search engines.